So hello everybody. Again, I'm Dustin Whittle. I'm a developer advocate at Uber where I help developers build moving experiences. And so thanks for joining me. We're going to be talking a little bit about how JavaScript is used across the engineering orgs at Uber. So many of you probably know Uber by now. Push a button, get a ride. It's really straightforward. And we've brought that to over 470 cities in 73 countries with more than 1.5 million partner drivers doing an average of more than 5 million trips a day. And so Uber's mission is really to make transportation as reliable as running water everywhere for everyone. And so we've been doing that for about 8 years now. It's become the fastest growing company ever. And so if you'll indulge me for just a minute, let's travel back to 2009 and take a look at what the first Uber app looked like. Not bad for its time, but pretty bare bones. There's a map, there's a button to order a ride. Pick me up, there's not much else to it. And then if we fast forward to 2012, aside from being more sleek and offering more products, we enabled more functionality, such as searching for a location, ETA estimates, and the ability to select different products. And that was 4 years ago. And then just last year, we did another refresh of the app, and now it looks a lot like this. And so we added scheduled rides, accelerators to known locations, and an interactive feed, just to name a few of the features. And so if you've used the Uber app today, it's much richer and more interactive than it was 7 years ago, or even 4 years ago. And our mobile platform team's goal is to ensure that Uber maintains a best-in-class app that's delightful and performant. And so let's talk a little bit about how we got there. So you can now play music with Pandora, see local recommendations with Foursquare, and even order food with Uber Eats. But it's not just rides. It's rides in choppers, it's bringing you kittens, it's ice cream, it's even Christmas trees. And so much more. It's moving people and things. And we did all of this while experiencing hypergrowth. And so this is a visualization of Singapore in 2013 through 2016. Sadly, the animation's not playing. There we go. So this is really, Uber started through this hypergrowth phase, and sort of this is what New Year's Eve, which is one of our most popular days, looks like year over year in Singapore. And so we launched our first ride in June of 2010, and we hit 1 million rides by 2012. And just a few years later, we hit over 1 billion rides in January of 2015, and we hit our 2 billionth trip in December of 2016. And so we've launched over 73 countries. And so just in 8 short years, we've built a lot of code, and a lot of this code is powered by JavaScript. So a little bit of the reason I'm telling you the backstory behind our growth and how we got here is to understand some of the lessons learned in using Node. We hired a lot of engineers. They wrote a lot of software. And in reality, engineering at a hypergrowth company like Uber looks a lot like this image. We're moving super fast. Almost every week, we're launching new cities. Millions of people are using our systems, and we don't have time to take the system down, not even for a minute of maintenance. So it's nearly like changing the wheels on a car that's running 80 miles an hour. And so when you think about how to structure an engineering organization, we have this concept of programs and platforms. The simplest way to think about it is that programs are built on top of platforms. Platform teams build the foundation and provide the technology building blocks to which program teams can launch consumer-facing products like Uber Eats and Uber Rush. And it's not all product teams. So part of our focus is to build a platform that interacts with the real world. And part of that adds a whole nother level of complexity. The physical world's complexity is infinite, but we only have 64 bits and less than 500 milliseconds SLA. And so what you ended up with was a lot of repositories and a lot of code. In fact, over 15,000 repositories powering over 3,400 microservices that power over 10 mobile apps. And we try to give this back through our open source SDKs and our open source repositories. And so Uber's ability to scale has come from high velocity, hard engineering, along with autonomous teams and domains. And so we really build a focus on developer abstractions that make it easy for developers to be productive at Uber. And so we use many languages. And part of the autonomous teams and autonomous domains is freedom of choice. So today we currently have 4 languages in production: Go, Java, Node.js, and Python. And these are really listed in order of preference today. And I'll tell you a little bit how we got here. So we're moving to Go and Java for backend services, but this is really a coming of age story, so I'm going to focus on JavaScript. So why did we start with JavaScript? Well, at first it was a small team, and we'd started on, like many great companies, on PHP, and that lasted about 6 months. And then it was time to evolve. And at the time, we were one of the early adopters of Node.js. We prototyped it at version 0.2, and we ran in production at 0.4. And so we chose it because it was a single stack for the front end and the back end. It created a simple interface with thorough documentation. So when you're hiring this many engineers very quickly, you need to be able to enable them. So you need to be able to onboard them to your existing systems, and you need to be able to find answers through documentation. And Node.js community was quite mature for even its age. And it lends itself to fast prototyping and quick iteration. It means it was easy to build at least something simple and then iterate quickly with a larger team. It's asynchronous, nimble, and flexible. So its non-blocking I/O made it great for building distributed systems like Uber is underneath. And it avoided concurrency challenges early on. And more, it had an increasingly mature module ecosystem. So you didn't have to implement all the functionality yourself. You could find a module that was slightly mature. But today we only use Node.js for our web applications. And I'll talk a little bit about how we got there. So again, Uber was one of the first companies to use Node.js at scale. And more money moved through the Uber application than anywhere else for a long period of time up until PayPal recently surpassed us. But why Node? Why Node originally? Well, there are really three core strengths. One is it handles asynchronous I/O with a non-blocking, single-threaded event loop, which makes it particularly well-suited for distributed systems that make a lot of network requests. And when you have a microservice architecture, you're making many network requests underneath, and you don't want to block on each one. And so Node.js, and really JavaScript in general, is excellent for quick iteration. It was really built for the browser, where the consumer is probably not the developer, so it was easy to silently ignore errors. But it means that programs can be inspected and errors can be addressed on the fly without requiring a restart. And then finally, a mature module ecosystem. The reality is that there was just tons of libraries available even early on. So I'm going to talk about 4 ways in which we're using JavaScript today at Uber. Through our marketplace platform, which provides the core services and the foundation for the Uber application. Through our web platform and all of our web presences. For visualizing data, at Uber we consume and produce a lot of data, but that data is useless unless you can visualize it and interpret it. And then through our developer platform, we expose our business primitives via an SDK that make it easy to build on top of Uber. But first, a little bit about our culture. So Uber invests heavily in developer productivity. Again, Uber's ability to scale has come from high-velocity, hard engineering along with autonomous teams and domains. And oftentimes, that means that we're shifting from a startup architecture over the last few years to a scalable architecture. And this isn't always easy. It really starts with the core infrastructure. The core infrastructure is probably most of you have the Google Cloud or Amazon Web Services. We use neither today, except for a bit of Amazon. But the infrastructure is focused on our compute, our network, our storage. And then on top of that, we have our developer experience. So our developer experience team really frees Uber developers to focus on making magic for our customers. It should be easy to set up a dev environment, to quickly bootstrap an application, and to deploy that application. And you should only focus on having to write the things that are special to your particular application. And then there's our marketplace platform. It's really an extensible platform for moving people and things. And so this is where all the core services flow through. And then on top of that, we have standardized foundation for building web applications through our web platform, a standardized foundation for building mobile applications through our mobile platform, and then we have an external API available for our developer platform where we expose and share all of our open source code as well as our API functionality. And so one of our cultural values is to let builders build. And we have over 12,000 full-time employees globally now. And so this is what it looks like to be an engineer at Uber and to quickly iterate and bootstrap a project. You start with scaffolding that's purpose-built for our entire stack. You start with a proposal, and you send this basically an RFC out to the entire engineering org for comments. So I want to launch a new service. So when I look up a place, I get venue data about a place. So you simply describe the service and some basic and abstract, the architecture overview, and then the timeline for how you want to implement it. And then you start with scaffolding that's purpose-built around our stack. A lot of tools don't solve for Uber's scale. So we built a bunch of tools, and we made it easy for developers to build on top of those tools. And then you deploy with standardized global infrastructure. And then finally, you scale your teams through playbooks. And so most companies probably have some service foundation. And again, at Uber's scale, this includes a bunch of functionality. So there's the asset pipeline for managing and deploying static assets. How do you make requests for data to backend systems through either HTTP or T-channel and Thrift? How do you handle translations and internationalization at scale? And then how do you store and retrieve data, manage network resources, compute resources, storage, logging? How do you manage performance testing and failure testing? And instrumentation, source control management, continuous integration, and then deployments, monitoring, and alerting. And so all of this is baked in by default. And so no app developers actually have to focus on this. It's built in. And so we'll first talk about Marketplace Platform, which a lot of the core services to the Uber trip flow are based on the marketplace, and so our real-time API. The dispatch system was originally built in mostly Node.js, meaning it's single-threaded, and Uber wants to take advantage of all the cores on a machine, but it also needs to be able to add new nodes to the system very easily to scale cities up and down. And so at a high level, it looks like this. It's pretty straightforward. The iOS and Android or web applications talk to the Marketplace Gateway, and then the Marketplace Gateway is really just a proxy to all the underlying microservices. And so we have services that are focused around business primitives or domains, like dispatching a rider to a driver to a rider, managing demand, managing supply, managing cost, authentication, etc. And so this is at a really high level, but the reality looks a lot more like this. And so this is really what it takes to get from A to B. Again, we have over 3,000 microservices, and more than 100 of those pertain to just the core trip flow. And maybe the services look a bit more like this, although I don't think you can read it. But the idea is that it's not really that simple. And so we abstracted all of this complexity away by creating a real-time API. And so the Marketplace Gateway is the real-time API for Frontlines, which is our frontline web service that all applications talk to. And it acts as a single router to all the underlying microservices by exposing over 1,000 HTTP endpoints, depending on the functionality that's needed. But it was a single place for exposing APIs, as well as dealing with monitoring and documentation for how to consume those APIs. And the Marketplace platform is really just the logistics challenge. It's how to minimize wait times for drivers and riders, how to maximize pickup efficiency in different areas, and how to combine the different logistics products, like managing Uber Pool, where you have multiple passengers in a single car, and managing Eats and Rush. And so really, the Uber Pool is a traveling salesman problem on steroids, if you think about it. How do I pick up one passenger, pick up a second passenger, and what's the optimal routes to drop them off? And maybe I can pick up orders for food in between time. But again, like many amazing web companies, Facebook, Wikipedia, YouTube, Yahoo, Etsy, it all started on PHP. And again, PHP is not necessarily bad, it fit really well for the time, and it was outsourced. So actually, if you looked at the original code, it was annotated with Spanish comments, which I find very interesting. And then in January 2011, this is when we started to adopt Node.js. We started to run into scaling challenges with the standard LAMP setup, and so we were trying to choose a new model. I don't know if you know, but at the time, Node.js and MongoDB were totally web scale, so it was going to solve all the engineering challenges. It turned out that wasn't really true. And so we also started to implement services in Python. And so for a long time, the core marketplace foundation was built on Python and Node.js. And then as we evolved, we basically maxed out our storage and dealing with our database, and eventually had to build our own solution on top of MySQL once we maxed out Postgres. And nowadays, we're moving more towards distributed applications with Go, Java, Node, and many different languages underneath. But again, let's focus on JavaScript. So monoliths aren't necessarily bad. Well, they're not bad at first, but they quickly turn into a ball of mud. And so they really optimize for development velocity of early stage projects. And they consolidate operational overhead into a single place. You only have one application to deploy and one application to monitor and manage. Monolith isn't really bad when there's a single team that owns it, but when you have a large distributed teams, all of a sudden you start to run into challenges. And we ran into some of these challenges building on top of Node later. And I don't know if you know this, but microservices are a thing. But really, a microservice is a thing that is focused on only one thing. But one thing doesn't mean one API. It means one business domain. And so most of Uber's architectural choices are driven by availability and performance, as it's easy for drivers and riders to turn to a competitive app. And so there's a couple of things we learned about dealing with monoliths and migrating a monolith to a microservice architecture, and I'll get into some more node specifics in a second. But it comes with the good and the bad. So the good is that there's clear ownership boundaries. If I have the service and I'm just responsible for managing authentication, I can focus just on that most of the time. It allows different products to move at their own pace. So each engineering team can move as fast or slow as it wants without blocking another team. So it allows the businesses to move faster. And it allows you to solve scaling issues, both the technical scaling issues, like making each service horizontally scalable, but also scaling the company in terms of making each team scalable. It also means that you can focus on supporting a single stack in terms of training, documentation, and tooling. When you onboard a single engineer onto a new team, they don't have to go through an entire boot camp. It also allows you to use the best tool for the job. So it gives people the freedom of choice by allowing them to use the language or platform that best suits that problem. And it increases the reliability of the system. It makes each service independent, it makes them each scalable, and makes them each testable. But it also increases the complexity. So there's a lot of issues. How do you do naming of services and discovery when you have 3,400 services and they're named haphazardly? How do you figure out what service does what? How do you handle discoverability of those services? Both the actual way to connect to the service, but also engineers just figuring out what's the right service to talk to build some functionality. And then eventual consistency. You can't have all the data in a single place in this setup. And then there's a performance impact, and as you build very large applications, it becomes troublesome to actually investigate performance and understand where the bottlenecks are. So distributed tracing becomes a thing. And so does testing. Testing becomes harder, because now you're testing not only every service, but the aggregate of all of those services. And then there's increased operational overhead. So with every single service, you need to deploy it, you need to monitor it, you need to test it and make sure it's instrumented and scalable and secure. And so these are a few of the lessons learned. And what we ultimately realize is that oftentimes this leads to repeated code and effort. And so when to choose between a monolith and a microservice largely depends on the size of your team and the complexity of the code base. And so Martin Fowler produced this great graphic that basically says for less complex systems, the extra baggage required to manage microservices reduces productivity. But as the team and the complexity of the application grows, you gain that productivity back by breaking the problems down into smaller pieces. And so we use many tools to build scalable Node applications, and I'm just going to talk about 3 today, and all of these are open source. And so we use these tools to basically build the backend services on top of Node. And the first one is Ringpop. If you think about the way Uber shards its data infrastructure, we use S2 from Google, which allows you to take a sphere like the Earth and break it down into smaller pieces in a consistent way. And so what this means that we're able to build to be able to shard on a city level. But some cities are more popular than others. So New York City and San Francisco don't fit in a single shard. And so at some point we maxed out our capacity and we need to add application level sharding. And so Ringpop allows us to solve this problem. So Ringpop uses a consistent hash ring that's also used by Amazon's DynamoDB or Memcache or React to distribute state across all of the different machines and to shard based on the city. And so we use this so that we can split up our services and make sure that not every piece of state has to be required in every level of every service. And one of the things that we also learned is that HTTP can be slow. And so at the time, Facebook had released Thrift, and generated code generally isn't great. But at the time, we didn't have support for Node.js and for some of the other languages that we use. So we implemented T-Channel. So T-Channel is a network framing protocol that's used for making RPC requests. It's a way of making requests for data to the underlying microservices. So even though externally we speak HTTP and JSON, internally we speak T-Channel and Thrift, because it's much faster and much lighter over the wire to use T-Channel. And I'll show this in just a few minutes. And then we also released Jaeger. And so Jaeger allows you to do distributed transaction tracing across large applications. So when you want to see the network calls that are being made to 100 underlying services, it's really hard to take a look at one high-level HTTP request and then to be able to understand the trace that happens all the way through the core systems. And so Jaeger allows us to do distributed tracing at scale. And so a little bit more about ring pop. So at Uber, engineering teams are already embedding ring pop into new projects for sharding, leader election, ordering, and into batching writes into a distributed database. And so we're now doing over 2 million RPCs per second at peak across our Node.js fleet. And so at the time, there was no need for an in-memory queue. And the basic idea of ring pop is that you have a Node.js application that lives in a single instance. This could be, think of it as a compute instance or a Docker container or just a EC2 machine. And so you deploy your Node application with an instance of ring pop. And it allows you to either decide to my application can handle this request, or I need to forward this request along to the right application service. And so this was the way of us implementing application level sharding. And so ring pop was originally is written in Node.js, but there's clients for several languages. And so the idea with ring pop is that you can just add the application, your application instance. Sorry about that. Add to your application logic a ring pop client, and you can decide whether each instance can handle a particular request or it needs to forward that request on to another instance. And so this was, again, our way of being able to expand and to make sure that when a service fails, it doesn't take out the entire application. It takes out at most a single city. And then, so this is what a Jaeger request looks like in the Jaeger UI. When you're building distributed services, observability is key. This way you can figure out what's wrong. Logging and exception tracking isn't enough because you actually need to understand what's happening in the underlying service. So in this case, this is a request to dispatch, and it talks to many underlying services, and you can drill down into each service and see its dependencies, and you can start to quickly figure out where bottlenecks are. When you have thousands of engineers working on thousands of services, you don't know if the problem is your own or somebody else's. So it's really hard to figure out the root cause. And so Jaeger makes this easy for us. And again, all of these tools are open source, so you can drop them into any project. All right, but at its core, Node.js is just a thin scripting layer on top of C++. So all the big boy tools just work. You should really learn how to profile your applications using Linux performance tools. There's no shortage of tools that provide visibility. And so if you look at things like strace or ptrace, Uber released Node Flame that makes it easy to build CPU flame graphs for Node.js applications. All the tools that you're already used to, you can readily use with Node applications. So a lot of people ask for performance advice, and my best advice is to just figure out how to profile applications on Linux. Most of these tools will help solve that problem. Okay, so some lessons we learned when scaling on top of Node, and some of the reasons why we primarily use Node.js for web applications today and not all of our core backend services. So you have to understand, at the time, Uber was doubling or tripling in size every year, and we were hiring faster than anyone's ever hired. And so we went from 400 engineers to just over, I think the official count is 13,000 full-time employees over the last 5 years. 6 years. That's pretty insane growth. And so one of the things is you give everyone the ability to choose their tool. And that works for so long as the teams are small, as long as a team can own their entire service, one team can understand the entire code base. Over time, you have much larger teams, you're onboarding people very quickly, and so while JavaScript's great to learn, it doesn't necessarily enforce contracts. And so this starts to matter. But the first thing that we found is the latency is too high for ultra-performant backend services. And we don't mean the average latency. We mean the 99th percentile for the max latency. When there's too much variance, it's hard to understand how performance will impact the end user, even if only one request out of 100 spikes. When you have dynamic languages that have dynamic garbage collection, it becomes hard to be predictable about performance and latency. And so we're starting to move towards Go and Java for the core backend services because we find that Go is much faster and Java has a very large ecosystem. Early on, it made it quick to iterate, but again, as the team size scaled, the developer velocity started to slow down. And part of the reason it started to slow down was because there's no interface, there's no standard contract. Microservices enforce a tight interface between them, and so when you have many large development teams, changing the way services interact or adding a property and removing a property and renaming things, It's very easy to break this. So using languages with static typing makes it much easier to catch this at build time instead of at runtime. And so we found that Node.js scaled until we hit about 100 engineers committing code to a project, and then it often led to more problems than it was worth at the time. And this isn't specific to Node.js. A lot of these are just specific to how you scale applications. Node.js is quick to learn, but it's also easy to write bad code. And so it's easy to make something functional and prototype. It's another thing to make it performant and scalable and to do it correctly. And so oftentimes I think teams found that it enabled you to move fast, but allowed you to be sloppy. And so over time we wanted to weigh on building quality, scalable code over quick iteration. And so I think that was part of the influence in moving away from Node for some of the backend services. And it also has a great ecosystem of small libraries that a lot of them follow the Linux philosophy of do one thing well. But then a lot of them are very immature. I think, I can't remember the package name that the author got a little annoyed with the NPM owners over a naming conflict and pulled it off and broke half the internet. Anybody know what I'm talking about? Right. So a single function can take down all of these websites, and so there are pros and cons with like this sort of module architecture and having this ecosystem of many small modules. And so Go and Java have more mature modules for most things, and so we started to understand that. And then something that a lot of people didn't understand is you can also just expose things through C++ in Node. And so don't be afraid to just implement things that need performance in C++. And so the Node.js HTTP client is notoriously slow. And one of the reasons is it could have just been implemented in C++. Okay, so let me just go back over this. JavaScript has a lot of easy tools that are bad for performance, like many closures or underscores for everything, and the clever features cost in terms of performance. So many people at Uber are under 6 months in, and most people just want to get things done. So they're not focused on making things perfect. They're making things work. And then Conway's Law. Any organization that designs a system will produce a design whose structure is a copy of the organization's communication structure. And so a lot of these decisions have just been driven by the way Uber's grown over time and the way the teams are distributed and autonomous. And so I think these are some of the basic lessons that we learned using Node.js at scale for backend services. And then some lessons learned that aren't specific to Node.js and just about scaling in general is that HTTP and JSON are built for browsers and clients. But RPC is better when you're talking server to server. And so the overhead of HTTP and JSON on the back end was too much for us. And again, the Node HTTP client was quite slow. And in our test, the T-channel thrift interface was 20 times faster than the HTTP JSON interface on the back end. And so this really started to add up, especially when you're making many network calls and gluing them together on the front end. After a certain age, microservices should become immutable. So once you've implemented a service, it's really hard to have people migrate off of that service or to change the interface to that service. So after a certain age, the idea is that you should just lock the interface to this service, and instead of rewriting it or refactoring it, that you should build a new service, which I think is contrary to popular advice of never rewrite a system, you should simply refactor it. I think because we break our problems into very small services, it becomes easy to replace them. Again, having multiple language allows for team preferences, but it also segregates developers based on their language preference and sometimes prevents the easy reuse of code across many services. And occasionally this could lead to politics. I think the idea of keeping the company first and foremost, your team second, and yourself last solves most of these challenges. And this is more of a cultural issue. Again, when you just allow 2,000 engineers to do whatever they want, sometimes it can be a little madness. And so at first, monorepos, having all of your code in a single repository makes it very easy to make atomic changes. But over time, it prevents the future open sourcing of smaller components and checking out subsets. And so there's a bunch of hacks around doing this at scale. We found that splitting out the repositories just makes it easier for everyone. And then performance problems are difficult to debug across multiple languages without standardized service dashboards and observability tools. So all of these tools, we have standard monitoring dashboards for pretty much everything. Most of you are familiar with the Elasticsearch stack. We use a similar piece, and we use Grafana. When every service comes with a standard Grafana dashboard that gives you key metrics about that service. But until we started doing this, it was really hard to get insights into what each service was doing because every team would build their own dashboard. And so it doesn't mean that every dashboard is usable. Sometimes it's business metrics, sometimes it's actual technical metrics that matter. And then ultimately, logging should never slow down production, and a failure storm, logging should just drop rather than delay. But the reality is when you're moving fast, it's easy to let the momentum carry you. And it's easy to just allow things to happen. Most of these are just trade-offs. Everything is really a trade-off. So you should be intentional about your choices. And when you're moving fast and you have lots of opinions in large teams, sometimes it makes sense to take a step back and decide what's the right way forward. And I think a lot of these lessons are learned in hindsight. And so I think this is a few ways that we use JavaScript on the back end to power our core JavaScript, our core trip flows with Node.js. And then, so now I'll talk about our web platform. So you've probably seen Uber.com, or maybe you've read about our self-driving cars, or signed up for a ride, or maybe just got an estimate, or even taking a ride with our mobile website that we just launched. Or you're using our city data to understand how traffic flows around cities, or you've ordered a meal with Uber Eats. Or maybe you just wanted to rush a suit across the city with Uber Rush. There's no shortage of websites, and now with new products being launched every day, like Uber Central, where businesses can offer rides on demand to its customers, or through our developer portal, my personal favorite is there's becomes a need for a standard foundation for building web applications. So the primary way we use Node.js today is for building web applications like this. And so I'll break down that stack. Our web platform team powers over 250 web properties, and not all of them are exactly this stack because it's changed over time. But without a consistent foundation, all of these applications would have been built off entirely different tools and architectures, creating a higher likelihood of security vulnerabilities, duplicated effort across teams, technical debt, and it would have meant the UIs aren't consistent. And so the web platform team was formed to support this foundation and prevent these types of issues. And at its core, it's based on Node.js, NPM, and Express. And we use React, Redux, and a bunch of other open source tools to really build the foundation for these applications. So at a high level, we start with these open source ingredients, and then we sort of build on top of them. And so we stand on the shoulders of giants. And oftentimes, Uber will, if possible, use an open source tool. And once we start to exceed its ability, we will write it ourselves or extend it and contribute it back. And so we started with this foundation, and let's dive into it a little bit. So we use Hot Proxy as our load balancers on the very front end, which is pretty standard. All the app servers are fronted with Nginx. This allows us to have middlewares that handle common things like authentication. Babel for transpilation so that we can use the latest JavaScript. Express as our application framework. React UI rendering, Redux managing state across JavaScript applications, Styletron for high-performance JavaScript styles, ESLint. It's really hard to get everybody to write code the same way. So if you have a lint and a standard set of style rules and continuous integration, it becomes easier to get teams of hundreds of people to produce consistently styled code. Browser for bundling client-side and server-side code, Tape, Enzyme, and Scion for writing tests, and then Gulp for build tooling. And so this is a pretty standard open source stack. There's really nothing spectacular or special about this stack. It's pretty common nowadays. But we added some special sauce to make this work for Uber. And so we have our own internal NPM registry that basically extends the open source NPM and adds caching as well as private package management internally. So we basically improved NPM to be much faster. We have our own tool like Yeoman that makes it very easy to scaffold apps with one command that have best practices and all the defaults configured. And so we don't use Yeoman, and I've removed some of the names of these just because some of these things are a little bit sensitive internally. But the idea is that you can bootstrap an application very quickly with a standard foundation. And then we have customized middlewares based around Express. So how do you handle authentication? How do you handle security by default? How do you handle collecting logs and metrics? As well as how do you have standardized internationalization, error management, analytics, etc. And so we want all this to be baked into the application by default. Not every program team needs to set up a new service and configure Google Analytics or to set up a new translation management system, etc. And then we have our own Bootstrap-like UI library that's built on top of React that provides React components for many different UI widgets. And so we've built this very early on. We were an early adopter of both Node and React, and so we've tried to consistently make it easy for developers not to have to reproduce a date-time widget or a map widget. And then we implemented our own RPC library for intelligently handling HTTP and T-channel requests, much like Facebook's Relay or Netflix's Falcor. And then we have shared build and test gulp tasks. So we have standard tooling and infrastructure for ES6 support, asset versioning, deployment pipelines, testing, analytics, linting, etc. And then we added universal rendering for the server and client. And so at the core of this web architecture is a bunch of open source ingredients, but we basically extended this stack to be purpose-built around our tools and our infrastructure. And so most of what's been added here really is no different than what you might extend in your world. How do you handle authentication that's specific to your application? How do you handle translations, etc.? And we also split our front end and our back end services. And there's a couple of reasons for this. One, the front-end services, those that actually serve web pages, from the back-end services, those that actually fetch data. So services can take advantage of universal rendering and also universal tooling. A lot of the tools that are available in JavaScript work on both the browser and the server side, depending on which problem you're solving. And on the back end, you can use languages that are better suited for the particular task. But it also means that you can horizontally scale each service independently. And then you can finally reuse the backend services across many things, like the mobile client, or expose it for the real-time API, or expose it through our external API for third-party developers. So you implement one backend, and then you can implement as many front ends as you want. And at a high level, our service looks like this. So inside the browser, you have a React-based app that uses Redux for state management, allows us to have a standard set of React components that interact through actions to our backend using standard Ajax, XHR. Some of this is a little contrived, but the idea here is simply that you split out what happens in the browser from the front-end service that actually talks to the browser, from the back-end service that talks to all the underlying microservices, and processes everything together. So how do you handle static assets? How do you actually make requests using T-channel and Thrift to backends? And how do you do that intelligently? And then how do you talk to the various data stores? And then how do you do all of this with universal rendering on the server and the client? And so I think you can see a little bit there. Moving a little fast as I'm running light on time. And then so we built React components for flexibility. Again, this is Uber's take on Bootstrap. We wanted to make it easy for developers to iterate quickly. And most of these tools are around two things. Developer experience, how do we make developers productive at Uber? And two, how do we make things scalable and fault tolerant? And so a lot of the engineering decisions were based on that. And so the ability to have React components made it easy to build beautiful sites with flexible components. I don't know if you've seen all of our websites, but they're all pretty amazing, and they look gorgeous, and they're very performant. And so it gave us standard UI components that were optimized for performance, that provided a consistent look and feel. And also it provided us the ability to have analytics and instrumentation baked in. When I can listen to a Redux state and automatically add analytics for user actions and set state, you get a lot of this functionality baked in by default that you would have had to otherwise manually implement. It also allows you to have seamless upgrades to new versions. So as we've redesigned applications, instead of having to redesign every single site, you could update the core framework and all of your components work as expected. And then, so Ryan on our web platform team outside of Uber wrote Styletron, and Styletron allows you to have high-performance CSS in JavaScript. And so he's actually also on our web platform team, and we use this at Uber to write and inject styles directly into the client side by handling everything at the JavaScript layer. And this allows us to really optimize for the critical rendering path time. and to build efficient client-side dynamic styles. And so the last thing I'll talk about in terms of how Uber uses JavaScript is to visualize data. Data visualization serves two main purposes, explanation and exploration, and these functions often overlap. And so we invest heavily in experimental tools and frameworks because we believe in the potential to enrich our users' lives. And we've already seen this from DeckGL, which I'll talk about in just a second, really improving the performance of teams. So this is a visualization that is built on top of DeckGL that allows us to take a look at the day in the life of Uber trips in San Francisco. So this is a 24-hour period of the Bay Area. And all of this you can do yourself. All these tools are open source. And so the skills of data visualization specialists span from computer graphics to information design, and we've launched a bunch of different visualization frameworks to make it easy for our data scientists and our visualization teams to work with data. And so again, all of these are open source, and you can check them out today at uber.github.io. And so we start with React Viz. This is really just a way to bind D3 charts to React components and a little bit more. And then we added React Map GL. So if you use Mapbox's GL, which we actually use for a lot of our internal mapping, this just provides a React interface for interacting with Mapbox. And then we added DeckGL, which provides a layered WebGL approach for visualization. And so the reason this matters is in that last visualization, there's over 2 million data points. And so when you start to have this large of a data set, it becomes very hard to be performant. And so using layering and instancing, we're able to increase the performance through DeckGL. And then LumaGL underneath is just an abstraction on top of WebGL. So again, you can check out React Viz. It's React components to render common data visualization charts like line, area, bar charts, heat maps, scatter plots, etc. as React components. And this is all open source and easy to build. We have many internal tools as well as external tools, and they're all built on React and DeckGL. And so this is a New Year's Eve in New York in terms of pickups and drop-offs. And so again, this is just another example of visualization built on top of DeckGL. And so you can see, one, they're super fast and smooth, but also they allow you to have 3D visualizations. So this is New York as well, sort of supply and demand in a 24-hour period over Manhattan, and what the trips look like throughout the day. And so all of these are built, again, on DeckGL. But it's made, DeckGL is designed to make visualization of large data sets very simple, and it enables users to quickly get impressive visual results with limited effort through the composition of existing layers. So we have a bunch of layers that we already have defined that allow you to just pass in your data and glue them together. And then we have LumaGL, which is just an abstraction on WebGL that's written in ECMAScript 6. And it's a component-based platform that also implements a 64-bit floating point emulation package that makes it very precise, even if JavaScript doesn't support it natively. And it also adds a bunch of tools for advanced debugging, tracing, and error checking on top of WebGL. And if you go to DeckGL, you'll see an example of, sadly the animation's not going to load here. But the idea here is that this is all the trips from between Yellow Cab and Green Cab in Manhattan. And this is all of Manhattan rendered with actual 3D buildings, as well as you can see the actual trips taken around the city. It's much better when the animation works. Okay, and at Uber we celebrate cities. We understand that every city is unique, so we really use visualizations to understand how cities are unique and to help celebrate cities. And so with DeckGL, with React Viz, with LumaGL, we really provide an open source foundation for both us internally as well as externally to build these visualizations on top of. And then lastly, I'll talk about our Uber Developer Platform, which is our external API. And we try to take the 3,400 microservices underneath and expose them as some core business primitives. Like I want to make a ride request. So you're familiar with push a button, get a ride? Well, you can do the same thing with an API call. Make an API call, get a ride. And then you can plug into the actual trip experience itself, as well as get information on drivers and manage deliveries. And you can do all of this with Node through our Node implementation. Take a look. I think that we try to invest heavily in open source at Uber. Not only is most of our foundation built on top of open source JavaScript, we've given back. And so you can check it out at github.com/ubernode for the Node.js backend tools, things like ringpop, Node Flame, etc. And then check out github.com/uberweb for some of the other tools, like our lint rules that we use internally. And then you can also see all the data visualization stuff at deckgl.com or uber.github.io. And not only do we pass along our code, but we also try to pass along our knowledge through our engineering blog at eng.uber.com. Like the learnings we've learned from using Node.js and for building visualizations. We actually, an interesting one for this crowd would be building the latest Uber Eats restaurant app on top of React Native. So not Uber Eats, the front-end app that I think most people would have on their phone, but the app that restaurants use because it runs on an iPad in a high-performance environment. We wanted to overcome some problems that we had building web applications. Like when you want to notify a user of a sound, the user needs to actually touch or interact with the application before you can take control of the sound. So we ran into a bunch of problems with that on the website, and so we started to re-implement in React Native. And so there's a great write-up on this on the engineering blog if you're interested. But Uber is no longer just an app on your phone. It's an open platform for building moving experiences, and we really want to encourage third parties to build on top of it. And so what future will you build? Find out more at developers.uber.com. And all of these slides come from people who are much smarter than myself. You can check out Matt Rainey's talk on scaling Uber. There's an upcoming talk on moving bits and atoms at scale. And then we're hiring everywhere around the world. So if you have any questions, please just get in touch. And that is all I have. Thank you.